Hello everyone, my name is André Santos and today I will be talking about our work on a high assurance ROS framework, also known as HAROS. But first, the problem. Writing robotics software is hard. There are many complex components that go into a robot, such as sensing, localization, navigation, manipulation, and so on. Not only are these components complex problems of their own, but their integration into a full system, into a full robot with a goal and a mission to accomplish is also not very straightforward. Some middlewares, like the robot operating system, provide an open source environment and mechanisms for the community to contribute with some of these components to solve some of these complex problems. However, integrating these components into a single system is always left to the user for each particular case. Now, software engineering is the skill that helps us verify desirable software properties using a variety of techniques, such as testing, runtime verification, model checking, etc. The problem with it is that often it requires expert knowledge that is beyond what roboticists know. And I mean this in the sense that roboticists come from a variety of backgrounds which may not specialize in software engineering. So our work has been focusing on this question, which is how can existing software analysis techniques and tools be used by non-experts, namely roboticists, to improve the software quality of ROS applications. So as part of the solution, we've been building this framework to analyze ROS systems called HAROS, the High Assurance ROS Framework. And it has been specifically designed for ROS users because, firstly, it takes source code, ROS source code as input, and then it reverse engineers or automatically extracts formal models as needed from the code. Lastly, using a high-level property specification language that we designed, users can annotate the formal models with behavioral properties. And this is a language that addresses ROS concepts directly, concepts that the users are already familiar with. So in this next slide, I show you a diagram illustrating the tool's workflow. It starts with the user writing down a project file. In this file, users specify the systems they want to analyze and annotate them with properties. Then this project file is fed to HAROS, which proceeds to locate the corresponding source code and ROS packages according to the specified project. From this source code, the HAROS tool builds the architectural model of the system or various architectural models of the system if multiple systems are specified in a project file, and proceeds to feed this information, source code, packages, models, to a series of analysis plugins, each providing a different analysis capability to the tool. In the end, HAROS produces a series of outputs containing issue reports, runtime models, runtime monitors, data files, and so on, depending on the installed plugins. To show you a minimal input example, here on the left we have a small project file that specifies 3 packages which should be included in the project and a single configuration or system called multiplex. This configuration shown here includes only a single launch file, which are ROS scripts to launch the system. And from this launch file and this configuration specification, HAROS is capable of extracting the model that is shown on the right, where green circles represent the message channels for entities to communicate, or topics, The white circles represent nodes, the processes themselves, while the purple circles represent shared parameters across the network. The HPL section that you see at the bottom in the left is optional and is where the users specify properties about a particular system. In terms of analysis, our plugins fit into various themes or categories. We have plugins for internal code quality, also known as linters, or tools that extract metrics from the source code, such as cyclomatic complexity, comment-to-code ratio, etc. Then we have architectural queries, or plugins that find problematic patterns in the extracted models, only at the graph level, not at the runtime level. And lastly, we have 3 types of plugins to verify behavior of the system, using model checking, runtime verification, and property-based testing. These plugins that deal with system behavior use our property specification language that I mentioned earlier. And to show you an example of this property specification language, here we have 3 small properties that illustrate its main features. In the first example, we see constraints over data. We have a property that states that messages on the bumper topic should never have a data field outside the specified interval. In the second example, we illustrate causality between messages and constraints over real time. The property states that a message will eventually cause another message to be published within a specified time window. Lastly, properties can also have scopes, meaning that the property will only be evaluated or verified within a particular system state, given by observing one message or 2 messages and defining an interval. So to sum up, the main goal of HAROS is to bridge the gap between robotics and software engineering, or rather, to make software engineering more accessible to roboticists. HAROS offers a variety of analysis, requiring as little user input as possible. And besides this, user input is iterative and partial. You can always add more over time. In terms of ongoing and future work, HAROS has been applied to various academic and industrial case studies, such as the Turtlebot 2, which is a widely known research mobile robot, the Carobot 4, which is a commercial personal assistant robot, and the Agrob system, an industrial agricultural robot for the hillside vineyards of the Douro region in Portugal. We also have planned adding support for ROS 2, which is now becoming the main version of ROS. And another interesting point is variability-aware analysis, including feature models. The goal of this type of analysis is to build essentially a family of products or systems based on their features, so that we can analyze once a specific family of systems and use the results of this analysis across all individual systems that are part of this family. Lastly, we are also developing new analysis plugins using different techniques and different model checkers, so that we can compare the results and select the best technique and tool for each situation. So essentially, that's it for my time, and I hope you liked this presentation about HAROS. I leave you here with a link to the tool, and thank you for your time.